Hello everyone, I welcome you all to this 30 days masterclass series on electric vehicle design using MATLAB Simulink. Today is day 27, gate driver design for MOSFET and IGBT. I welcome you everyone here. Yes, I welcome Amisha, Kota Lavanya, Avin Soni, Venkatri Praveen, Soni, Hitesh, Gautam, Karan Ravi, Paraful Natya, Ashwini, Nelson. Welcome participants, warm welcome. Yes, Pranav, Akshay, Prashant, Ganesh, Karan Ravi. Good evening everyone here. Natasha, good evening. Sushil, good evening. Deepak, good evening. Aditya Kumar, yes. Very good evening, participants who are all present here. Yes. So I hope you have enjoyed the previous class. So today we are going to discuss about gate driver design for MOSFET and IGBT. So do you have any idea about what is gate driver? Do you have any idea about what is gate driver design? Thank you, Gautam. Good evening, Dr. Govindraj, Karthik, Hariharan, Shivateja. Do you have any idea about gate driver design? What do you mean by gate driver? So can you please anyone comment here? Good evening, Maheshwari. Yes, I'm waiting for a replic, participants. No, Shivateja, no. PWM, Aparna job, yes sir. Can you just comment what is gate driver? PWM, Sekumar, Ratna Raju. Good evening. What do you mean by gate driver? A gate driver is a power amplifier that accepts a low power input from a controller IC and produces a high current. Yes, exactly, Mr. Gautam. Yes, exactly. That's the gate driver. Yes, anyone others? Provide gate pulses. Same as MOSFET. No, it's not exactly. Any others? MOSFET or IGBT? So the gate driver, simply we can call it as an isolator, because our PWM generator is our microcontroller, right? And the power circuit will handle the huge amount of current. Suppose if you take a 1 kilowatt motor, then if you take a 72 voltage terminal voltage, so in that case obviously the current will be about 10 to 13 ampere. So that 13 ampere should not flows into the microcontroller, because the microcontroller is a low power circuit. Because the microcontroller, if any fault currents or any noise is available on the microcontroller ground, then the microcontroller will get hang. So to avoid that one, so we have to introduce isolator between the circuit, between microcontroller to power circuit. So that is the main objective of this gate driver. Right? Yes. Thank you. Thanks for your comment. So let us move to the topic. And about the Pantech is an educational equipments manufacturing company. You can get lab equipments for EEE, ECE, computer science, IT, and AI, robotics, IoT related products. You can get it. and our vision is to help 10 million students to learn the technology in easy way. So far we have trained about 1.5 lakh students. So this year we will finish it the 10 million students. And see, actually if you take a application block diagram, see here, this is the load, which means that either a motor load or battery. If you take a OBC model, that is onboard charger model, so in that case power circuit will be the DC to DC rectifier and the load will be the battery. If you take a motor control applications, so the load will be a motor and then power circuit will be a inverter model, and then input will be a DC bus voltage, right? So now the power circuit will be the combination of SCR or triac or MOSFET or IGBT or GTO or SiC MOSFET or GaN devices, right? So this is the combination of any one of this device. And then now you have to generate a PWM from the microcontroller. So the PWM microcontroller is always a low power circuit. So can you tell me the approximate maximum current which can be drawn by the microcontroller peripherals? Can you tell me any approximate current which is drawn by, if you connect one LED to the microcontroller, so how much amount of current can draw from the microcontroller? How much amount of current you can draw from the microcontroller peripheral pin? Like if you take a GPIO port A0 pin, if you are connecting one LED to the pin, then how much amount of maximum current you can draw? 40 milliampere. So that is the maximum amount of current. So the 10 milliampere will be the nominal voltage. So nominal current rating. Right, 40 milliampere, it's too much amount of current. So 10 milliampere will be the maximum amount of current. And so here, if you take a power circuit, so in this power circuit, see, let us assume that the load is 1 kilowatt. The load is 1 kilowatt. So let us assume that terminal voltage is 70 voltage. Then in the case, the current rating will be like a 12 ampere maximum, right? So the 12 ampere. See here, the maximum operating current will be like a 10 ampere, 10 milliampere, right? And the operating voltage will be 5 voltage sometime, or else for the micro FPGA 1.6 voltage or 1.2 voltage and DSP 3 voltage. These are the operating voltage for the PWM generators. See here, the 70 voltage circuit with a 12 ampere current. So there is a possibility to flow into the microcontroller part because this ground terminal. So these two grounds can be interconnected. Then only you can pass the PWM signal to the power circuit. So in that case, there is a chance to flow the path. In the return path, the current can flow into the negative, microcontroller path also. So comment in the comment box. If you are clear with the point, you please comment in the comment box. If you are clear, please comment in the comment box. Yes. So in terms of microampere. Yes. So now we have to introduce the gate driver circuit. So first you have to choose the device. So based on the power circuit, you have to choose the device. And second model, based on the power circuit, suppose if you are going to choose the SCR, then one gate driver circuit we have to use. Suppose if you are using a triac, so actually both are similar category, like SCR and then triac will be the similar category. And similarly, MOSFET and then IGBT, other devices comes under the similar category. And here, based on the frequency range and then current range, we have to choose the power circuit. We have to choose the gate driver circuit. And finally, you have to consider about the target applications. Like, is it a highly inductive load or it's a pure resistive load? So based on the load also, we have to consider while you design the gate driver circuit, right? And now we should know the isolations. What is the isolations? The isolation electronically we have to separate both the ground. Both the ground, nothing, power supply ground as well as the power circuit power supply ground, power circuit ground. So these two ground needs to be isolated. So these two grounds needs to be isolated. So now what do you mean by isolation? How you can introduce the isolations in the electronic circuit? So how you can introduce the isolation into the electronic circuit? So do you have any idea? Okay, so now let us understand the yes, optocoupler. Any other device? Any other device? Optocoupler. And one of the another component also there, so I will tell you not connecting by diode, so that is not isolator. So I will tell you one by one, so please keep engaged with entire class. Yes, Swati, isolation transformer, not a transfer, transformer. Yes, so to understand the isolations, to understand the gate driver circuit, you must know what is the MOSFETs, what is the solid state switch. Already we have discussed in the same concept. So actually, if you take ideal switch, this is the ideal switch. If you press this switch, then you will connection will get turned on, right? If you press the switch, then the circuit will get closed. So in that case, you will get the output. Similarly, for the solid state devices like SCR or MOSFET or IGBT, if you apply a voltage between the gate and then source terminal, if it is a MOSFET, for IGBT it will be this emitter terminal, for SCR and then gate and then cathode terminal, right? So if you apply a gate pulse, so if you apply gate pulses between these two pins, then the circuit will get closed. So in that case, the current will get turned, passed via this circuit. Simply you can understand this switch. So now what it will happen when you apply a voltage to the devices. See here, whenever you are applying a gate pulse to the any devices, right? So internally there will be a depletion layer. So the depletion layer will get removed whenever you are applying the voltage. So if you are keep on increasing the gate voltage from 0 to maximum, so whenever it is maximum, the circuit will get closed. If it is a minimum, then the circuit will get opened, right? So this is very simplest animation video to understand the working principle of solid state switches. So whenever you are applying a gate pulses, the two terminal will get connected. So whenever you are removing the gate pulse, then the two terminal, the connection established between the anode and cathode will get removed. So now let us take the power circuit. What are all the powers for what power circuit? What switches we have to choose? For AC to DC rectifier, SCR needs to be selected, and AC to AC and again AC to AC voltage controller, the triac device is going to select. And DC to DC applications, MOSFET we can use it, and DC to AC applications we can use it for the IGBT, right? And how you can choose these devices, so we will discuss in the forthcoming slides. Keep engaged with the entire class. So now what is the power circuit applications? Where we are going to use the power circuit applications? AC to DC, nothing but the rectifier. See here for DC power supply and then front end rectifier, motor control, DC motor control, we will use a rectifier model. Similarly, AC to AC voltage controller, motor control for low power applications, or else AC voltage motor controller, and fax devices and heating applications also we will use the same concepts. And similarly for the DC to DC converters, DC regulated power supply and DC motor control applications, and high power SMPS applications we will use. And DC to AC inverters, this is called the inverter, whereas for domestic inverter, low power motor control, and then high power motor control, high power inverters, wireless power transmission. So for these things we will use a DC to AC as an inverter model. So here you have to choose the device. For SCR, For in the rectifier, we will use the SCR, right? So this is the SCR model, TYN612 or BT137155. So these are all the switch name to choose the devices. Similarly, MOSFETs. So here IRF 250, IRF 840, and IRF 560, 460. So these are all the devices, which is major manufacturers are international rectifiers, and then Semicron and Infineon and microchips also. I think some MOSFETs they have released. I mean in Texas Instruments and ILX. So these are all the guys you can get the device from this one. And similarly the IGBT, right? So IGBT also it's one of the device, so you can use it. And apart from this device, latest device is called the SIG devices and then GAN devices. The SIG devices, wherever you need high frequency applications, you can use the SIG devices. And similarly, wherever you are going to have the voltage, so in that case, you can use the GAN devices. And this for your applications, right? So this is the frequency range. While you choose your device, there is a two major parameter. One is called the frequency, right? The frequency, nothing but that you are switching frequency, right? And similarly voltage, that is called operating voltage, and current also we have to take care into the consideration. See here, if you take a 1 kilowatt load and voltage range is 100 voltage, right? And then 10 ampere. See, so let us take this case study. 1 kilowatt, 100 voltage and 10 ampere, right? So this comes under that 1 kilowatt. So now you 100 voltage. See, let us assume that this is the 100 voltage part, right? And what is your switching frequency? Suppose if you are going to take a DC power supply, DC to DC power supply, right? Suppose if you are going to design your onboard power charger, more than 100 kilohertz, right? More than 100 kilohertz. 100 kilohertz. So this is called switching frequency. Similarly, if you take a DC to AC applications, so in that case, the switching frequency you cannot move more than 100 kilohertz because your inverter power loss will be huge. So in that case, you have to reduce to the switching frequency. So what do you mean by switching frequency? The frequency rate of the carrier pulse in the sine wave width modulation, right? The fundamental pulse width fundamental output AC output will be 50 Hz, whereas the carrier frequency, right? We have discussed the inverter in the inverter class. The carrier frequency is the switching frequency, right? In that case, let us take 10 kilohertz. 10 kilohertz for the same power rating, 1 kilowatt. For DC to DC applications, you have to use the switching frequency 100 kilohertz. Whereas DC to AC applications, you have to use a 10 kilohertz. Suppose if you take a case 1, for DC to DC 100 kilohertz, you have to choose the MOSFET. See here, this is the line, and then frequency like here 100 kilohertz will be there, right? So 100 kilohertz. So here you have to choose the MOSFET. Similarly, for DC to AC, the same voltage range, 100 voltage with a 10 kilohertz. See here, less than 10 kilohertz. So here you have to use IGBT model, right? Is it clear? Is it clear? Is it clear? So how you can choose your device for your applications? How you can choose your device? Super. If you have any questions, you please ask me. And if you are working any circuit, you just give me your rating. I can suggest you how to choose your device. Super clear. Super. Thank you. Thank you, comments. Thank you, participants. Yes. So if you are working in your applications, you just charge, give me your rating. I will give you how to choose the device. Yes. Right. So here we have discussed two case study. How to control switching frequency. Why you want to control the switching frequency? Where you want to change the switching frequency? Yes. If you have any more questions, you please ask me. 500 wattage, 448 voltage, SR. So here, how much switching frequency you are going to use in the see here the for 500 voltage you can choose the IGBT, and suppose if you are switching PWM frequency is less than 10 kilohertz, you can use it IGBT. If you are going for the high frequency, then you have to go with and similarly if you are going to use a high power voltage, right, the 1200 voltage, 400 voltage, then obviously you have to choose the MOSFETs. I want to make a 100 wattage solar charge converter. Which is the best? 100 wattage for the rating, for 750 wattage and then 48 volt IGBT. You can go with the IGBT. Yeah, with the switching frequency, you can change the speed of the DC motor. 200 voltage LED driver. So here you have to understand the switching frequency. Always you should identify the switching frequency. For DC to DC applications, keep switching frequency is high, whereas for the DC to AC application, switching frequency must be less than the 10 kilohertz or 20 kilohertz. Fast switching damages the MOSFETs. That's why I am asking how to control the switching control. See here, the PWM will not damage your MOSFETs. If you are choosing the proper MOSFET based on the data sheets, you can check the data. The PWM will not damage your MOSFET unless if you are generating PWM. Suppose if you are taking the two switches on the same leg. Two switches on the switch 1 and switch 2, you cannot switch on the two switches at the same time. So in that case the MOSFET will get short circuit. So you have to identify if your PWM pattern is properly working and then it's logically working, then the MOSFET will not get damaged. Right. So let's move to the key takeaway from the slide is based on your applications and then voltage rate and then frequency, you can choose the component. You can choose any devices, any make, right? So let us take the simple case study. See here for 2000 kilowattage and then output voltage is 230 voltage and then ampere rating is 9 ampere and then frequency is that 50 hertz. And the voltage is that 325 voltage and then 450 IR frequency, switching frequency is 4050 hertz. So this is another example. Heat dissipation, I will share you one more video. So you just check that video, you may get a clear idea about it. I will share you that notes. And see here, let us take this case study and see here the safety factor. See, for the safety factor always you should choose like for domestic applications, like suppose if you are going to design your home inverter, the safety factor will be 1.5 times. See here the 230 voltage with 1.5 times. So let us assume that 450 is the voltage rating. and here the current rating like 9 volt 9 ampere with 15 ampere, so the 10 ampere, so 1.5 time like 15 ampere, so that is the maximum current rating. So because you have to follow the safety factor, unless you have to lose your money. So for instead of 1.5 safety factor, if you are keeping 15 is a safety factor, in that case the cost rating cost of the device will be huge, right? And see here in that case, and similarly for the marine defense applications, you have to keep the safety factor at 15 times higher than this normal rating. Now you have to choose the device, right? So from in this one, if your switching frequency is 40 4000 kilohertz, in that case MOSFET is low power MOSFET is enough. So like most low power MOSFET like IR of 460 will be the best choice for this rating, right? Because for these applications, so the lies between here, so this is the 200 voltage something, so IR of 460 you can use it. Suppose if you are going for the 600 voltage, then you have to go with the IGBT, right? So now gate driver property. So what are the gate driver should have? So first one is that isolator, and another one is that amplifier, that is the gate current. Based on the gate current you have to choose the amplifier, and speed up mechanisms. See here, if you, instead of gate pulse, suppose if you are applying the gate pulse at here, in practically it will not be like this, so it always will be a huge slightly variations. So like that it will be. So we have to reduce this time, that is called transient times. And the peak current, so whenever the depends the decoupling capacitor which is available on the gate to the source component, so there we have to consider that capacitor currents, that is called a driver peak current, and fast short circuit protections, and then active Miller clamp effect. So these are all the points we have to consider in the gate driver circuit. And also shoot through protections. Do you know what is shoot through? So shoot through nothing but the short circuit. So these are all the additional features you have to keep in your mind. So now again these are all the protections. So like overcurrent, and then fault circuit shutdown, and these are the additional protections you have to keep in your circuit. To ensure all these facilities, we have to introduce the electronic circuit in your gate driver circuit. So now you should understand the MOSFET structure technology. So there are three different MOSFET structure technology. So generally we will call it as like a V groove. So V groove trench technology. So this is for each and internally in the MOSFET. So there will be a different type of layers, like a positive layer and the negative layer, photons layer and then neutrons layer, and everything. So actually each and every layer will be mounted and fabricated on the based on the die for the FET components. So a very famous one is that V groove trench technology for getting the high efficiency, right? So internally for each and every layer, like suppose if you take this one, gate to an oxide layer, so in between there will be an internal resistance. So that's why we are calling as a on-state resistance and then off-state resistance. Whenever the MOSFET is getting turned on from off-state to on-state, that is called on-state resistance. During that time only that resistance will come into the picture. Similarly for the off-state resistance. So these resistance are the causes for the on-state switching losses. See here some equivalent circuits which is used, which is derived based on the technology which the MOSFET developed, right? See here, these are all not physical transistor elements. but due to the solid state material, the properties will introduce these components, resistance, and this is called the Miller effect, capacitor. Similar, this is also, and this capacitor, and then inductors, right? So these are all the on-state electronic effects which will be occur during the transient periods. All right. So now let us take this one, and we can try to understand the concept how if you are applying a gate pulse from 0 to 1. So this is called on-state transient. Whenever you are applying the voltage, so this voltage will flows into the two circuits. One is called this capacitor and this capacitor, right? So during this period, the capacitor will try to charge. So in that case, if you are applying DC voltage to the capacitor, what it will act? So it will act as a switch. Initially, the capacitor will act as a short circuited. So in the time the circuit, the capacitor will pull more amount of current from the source. So let us assume this is the source and this is the load. So this is the source and this is the load. So whenever you are applying the gate pulse to 1, so during this transient, this capacitor will try to draw more amount of current from the source, because our microcontroller, see, actually the PWM generator is what? The PWM generator is a microcontroller. So microcontroller maximum operating current will be 10 milliampere, right? But whenever you are increasing the device rating, like 500 voltage with 10 ampere or 20 ampere or 50 ampere, if you are increasing the current rate, similarly the internal capacitance of the device will get increased. So due to that one, the initial current will be huge amount of current needs to turn on the device, right? So in that case, you have to supply a sufficient amount of current, so that information will be available on your data sheet, right? So is it clear? If you have any questions, you please comment. Is it clear? If you have any questions, you please comment. What is the difference in shoot through and then short circuit? The shoot through is nothing but manually we are going to generate the switching pulses to short circuit in the same leg. So for avoiding that short circuit current, we will introduce the LNC component to manage the shoot through logic. So in that case, for the boost mechanisms, we will introduce a short circuit. Short circuit nothing but that is the faulty mechanisms. Thank you, participants. So now let us understand the graph. See here, initially you are applying the gate pulse voltage. So here, if you are applying the gate pulse voltage like square pulses, so in the real time, it will not be a exact square pulse. So always it will be a linear voltage. So initially the gate current will be huge because of the particular capacitor, and after that, so the till that after the threshold value of the gate source voltage, still it will keep on increase, and again initially the gate current will be peak, and after that it will try to get reduced, right? Whenever after the threshold gate voltage, see here the drain current will starts to increase from 0 to maximum. The drain current till the drain current, actually here at this instant itself you have applied the voltage, the gate voltage has been started, but the drain current is not started, right? So this is the ultimately we have to ensure that the drain current should be high, because we are turning on the particular switch. Still that the drain to source voltage will not reach to 0, and once if it is the capacitor voltage fully charged, and after that only the drain to source voltage will get approaches to 0, and the drain current will be increased maximum. right? So this is the actual mechanisms. So when after the drain to source voltage reaches to zero, and during this time only the gate current will get reached to zero. Not a zero, it will be minimum current will be there, minimum sufficient current will be there, right? And after that the gate to source voltage will be maximum. See here we have the ideally we have to say like this, the gate voltage will be like this, but it will not be practically, it will not be like this. So it will be always, it will be keep on the linear stage. So this period, right, so this period is called the turn on delay time and rise time, right? So here in the data sheets, if you take this device IRF P250N BF, so this device here they will mention like this, right? The turn on delay time, so this is called the turn on delay time, so 14 nanoseconds, and then rise time, so this is the rise time. So rise time, so this will be the 43 nanoseconds. So here if you take a 43 plus 14 nanoseconds, like 44, 47, 57 nanoseconds, you cannot identify, you cannot fix your switching frequency less than this time to turn on this one. Similarly for the turn off mechanism, suppose if you take a 10 nanoseconds, 16 nanoseconds as well as 16 nanoseconds, so like 120 nanoseconds, so you cannot use this device for the 120 nanoseconds switching frequency. Always you should have a higher switching frequency than this one. Is it clear? Is it clear? So just ask your questions. Please ask your questions. If you want to repeat, please just repeat the video. If you have a questions, you please straight away you can ask me. I will try to give you the answers. Yeah, thank you. Similarly, for the turn off mechanisms, see if you are turn offing the pulses, right? So if you are removing the pulse, if you are removing the pulse, see the first the capacitor will discharge the circuit. So because actually it's already charged one, right? So the capacitor will discharge the circuit. The same procedure will be repeated. See here, if you are removing the gate pulse, see, which means that we have removed to the zero, but it will not be reached to the zero level. So it will be there till the threshold value, and after that it will approaches to zero voltage. So this is called turn off delay time. This is called the turn off delay time, and this is called the turn off fall time. So not a rise time, this is a fall time. See here, turn off delay time and then turn off fall time. See here, so there is a time difference. 14 nanosecond is the turn on delay time, whereas here turn off delay time is the 41 nanoseconds, and then rise time will be 43, and then fall time will be 33, right? So you have to combine all these things. So based on this one, you have to choose your device. Yes, so what is the effect of parasitic capacitance? So this is the Miller effect or parasitic capacitance. So due to this parasitic capacitance, the parasitic capacitance is nothing but it's not a physical capacitor. Whenever you are applying voltage to the particular terminal, so due to that solid state material property, that material will act as a capacitance. Right, so it will try to draw more amount of current whenever it changes its states. That is called the parasitic capacitance effect. Thank you. Yes, so this is called SCR characteristics. You must know the basic characteristics of all the devices. From this only you can identify your gate device, gate drive circuit, right? So see here, if you are increasing the gate current, so that is the gate current. Initially the gate current is less and then high. If you are increasing, keep on increasing the gate current, by increasing the gate to cathode voltage, then we can latch the device. Otherwise, we cannot latch the device. Similarly, for the MOSFET, if you are increasing the gate to source voltage, then we can increase the drain current. Otherwise, we cannot increase the drain current. And this is the IGBT also. Same procedure for the IGBT. And in the IGBT, for the low frequency, there is no issue. Whereas if you are going for the high frequency and high current applications, you have to introduce the negative pulses also to turn off the MOSFETs. See, instead of the square pulses, you have to keep negative pulses also. So due to this negative pulse, we can pull down the MOSFET to the off state and very quick for high power current handling circuit. And so isolations. So these are all the first device is called optocoupler. So based on your switching frequency, you have to choose this device. And second one is called the galvanic isolations. That is that isolation transformer or pulse transformer. For SCR, you have to use this pulse transformer. Whereas for the IGBT and the MOSFET, you can use the optocoupler. What should be the minimum watch hours on LMS portal? So just watch all the video to download the internship certificates. What is the thumb rule of selecting the device rating? First, you should identify your circuit power rating. So if your power rating is 400 voltage 10 ampere, in that case you have to choose 600 voltage device or 800 voltage device with 20 ampere. So just double the device rating, then you may arrive the device rating. And similarly, while you choose the switching frequency, you should identify the data sheets on time, off time and all. So can we use IR of Z44N in voltage control circuits? Yeah, you can use it. You have to ensure the device current rating based on your application circuit rating. And next property is amplifier. See here, this is the totem pole amplifier. So this amplifier only is going to give you the sufficient amount of current. Suppose if your gate current requires 2 ampere, the gate requires 2 ampere. So in that case, so this power supply, actually my microcontroller will not supply a 2 ampere, right? The microcontroller will not supply 2 ampere. But our amplifier circuit will supply a 2 ampere, because this totem pole amplifier, that is the common emitter amplifier, will generate whatever the available the voltage. That is that suppose if you are giving the 2 ampere with the 15 voltage power supply, that is the gate driver power supply. So the exact 2 ampere we can draw during the on time. So during this on time we can draw this amount of current. Alright, so this is the totem pole amplifier. Similarly, so this totem pole amplifier will give you the perfect solutions to draw the exact maximum amount of current, and just 2 transistors is enough to achieve this one. And similarly, it has a high reverse breakdown voltage protections, so your gate driver will not get fault. And the protections nothing but in the gate driver we have to ensure the protections, right? So this is called the Zener protections by implementing to ensure your protection circuit. And similarly, this capacitor will suppress the peak voltages. Yes. And next one, the dV by dt protection ratio. See here, let us take this is the gate driver, MOSFET. So here we have to use the RCD, that is resistor, capacitor and then diode. So this RCD you have to use. So for calculating the capacitance and the resistance value, this is the formula to calculate the RCD value, right? So this is the C into delta V naught is equal to delta I naught, right? So from this capacitance I naught, that is I into the range delta T divided by delta V. So the I nothing but the gate current, like how much ampere, how much drain current, how much amount of current is going to draw. Similarly, the switching voltage, switching frequency, that is the range of time. And similarly, delta V nothing but the change of the voltage, that is the maximum voltage, right? Similarly, you have to apply this one. So just apply this one, you can get a power. And similarly, see here this resistance, that is that 4.7K pull down resistor. So this resistor also you have to keep to introduce the dV by dt ratio. So if there is any spike, then you can remove the spike with the help of this resistor. So these are all by experience only you can implement in your circuit. But for initial level, you may feel some difficult to understand these concepts. Whenever you are facing the problem, actually even though all the logics are perfect, but still your device is getting failed, then you have to introduce these concepts to ensure your circuit operations. And how to increase the turn off speed mechanism. See, if you increase the, if you put one resistor, one diode in anti-parallel with a resistor, then we can increase the turn off speed mechanisms, right? And here this is the PCB consideration. So while you design the PWM circuit with the gate driver, then you have to implement one minimum current flow path. So that will reduce the inductive issues. Otherwise, here the inductive issues will be there. So due to that, the ground will get heavy noise. Yes. Just use these notes to get closed. And high frequency isolated driver. So actually the scale-i driver will give you the perfect one. So here the scale-i driver, like more than 200 kilohertz, 250 kilohertz. So just to visit this website, scale-i driver in this Google, you can get a lot of devices under this one. Aravindan, that is not possible. So you have to take care about your attendance, because always we'll keep only the email ID, not other things. We cannot go and check in the detail email ID. We cannot ensure your circuit. So please take care about your email ID to ensure the attendance number of times, 25 times. The isolation transformer nothing but not a usual transformer, it's called a pulse transformer. So there 1:1 transformer, there will be ideal loss will be very negligible amount. Thank you, Vicky. If you have any questions, you can ask me. And this is the MOSFET driver, simple driver, which is working in our laboratory. So just to take this note, and the internship people, you can download this actual schematic from the LMS portal. And these are some type of drivers you can use it. Just visit this download the presentations from the LMS portal. I have given the each and every link. Just to visit the link, you can understand more about it. So this is called high side driver, nothing but if you take a 3-phase inverter, so 3-phase inverter, so these are all the high side drivers. Similarly for the low side drivers also, separate low side driver also there, right? And from the Pantech you can get a 6 individual driver. This driver will be compatible for both IGBT as well as the MOSFETs. And single channel MOSFET gate driver also available. So simply you can buy the board from the Pantech and then you can use it for your research applications. So no need to worry about the driver circuits and all everything. Simply you can connect your input AC DC 15 voltage and you can start using this MOSFET for your as per your topology. And 2-channel driver also available, so no need to worry about for the individual circuits and all. Even single channel, 2-channel, and then 2-channel with MOSFET or IGBT, whatever you want, we will give you. And a 6-channel inverter or 6-channel inverter with MOSFET or IGBT as per your current rating, we will support you. And then TLP 250 driver board. So this also you can get it from the. If you want these boards, you please just WhatsApp me. I will give you the board, sir. Price details and that. And 100 ampere IGBT gate driver. If you want to handle the 100 ampere, then you have to use this kind of driver, because this driver will enable the negative voltages to ensure your turn off mechanism of the IGBT. And 2-channel SCR gate driver. So this is called the pulse transformer. So earlier we have used the optocoupler. So this is the pulse transformer to ensure your output voltage. And so this is Kuiper Semicron gate driver board. So you can simply buy the board from the Pantech and then you can use it for your applications. And now you can ask your questions. Thank you, Abhishek. How many days? As of now, 1 week of time, you can get the product. Thank you, Abhishek. Thanks for your comment. If you have any more questions, you can ask me. Certificate. I already told that after 30 days, like 25th, you can get a certificate by email. We will send you the email. We will consider only the email ID. That email ID, how many days it is presented. That is simple logic. If you have any more questions, you can ask me. Is there any flyback capacitor? Depends the topology, we have to choose the device. Thank you, Israel. If you have any more questions, you please ask me. If you have any more questions, you please ask me. Thank you, Sharath. Nilesh, we will send you the certificate by September 25th. Certificate September 25th. By email. If you have any more questions, you please ask me. Thank you, Vicky. If you are interested, and one more thing, if you are participating this webinar, so this is the last chance to convert your webinar certificate into internship certificate also. So if you are interested, you can join the internship and then you can immediately on September 25th, you can get our internship certificate, and till that time we will generate the certificates, internship certificate. So this webinar attendance will get calculated for the internship also. If you are not, so till now, if you are not enrolled into the internship, there is a chance to get your internship certificate on 25th. For this one, no need to watch the LMS portal. So for this, attendance will be calculated for the internship. So that is your biggest chance. So those who are all interested, you can join in the internship. Thank you participants. Thanks for your valuable time here. If you have any more questions, you please ask me in the comment box. I will try to give you the answers. Thank you once again. We will meet you in the next class.